So let us start with our discussion on the various overvoltages in a system, and we will start with lightning overvoltages, which is an external overvoltage. Now, how does lightning occur? Essentially, lightning initiates from a cloud. A cloud, a charged uh, cloud generally has negative charge, and it holds negative charge because of the moisture, because of the ice particles inside within the cloud, and they are generally at the bottom of the clouds. You have charge centers. Let's say you have negative charge centers. Let us see how that negative charge center can result in lightning. The first thing that would happen is, let's say you have this charge center, and because of this charge center, there would be induced charges on the earth. Now remember, earth is a perfect conductor, but when you have, so it's supposed to be able to conduct away all charges when connected to it. When you have over the ground a very large quantity of charge floating with the cloud, then there would be induced positive charges on the ground. As a result, there would be a very high electric field between the cloud and the earth. And therefore, in the region close to the cloud, there might be the development of ionization channels, and there might be stepped leaders which are propagating. So the lightning discharge begins to propagate by ionization of the neighboring air in a stepwise manner. So by stepped leaders are formed. And out of that, there will be a pilot streamer. The pilot streamer and the stepped leader causes the lightning, that causes the discharge to propagate earthwards, and there will be outward branching of streamers to the earth. The net effect of this process, this first step, is the lowering of the charge that was originally in the clouds into the space beneath the cloud. Now, as this process continues by stepwise propagation, there will come a situation where the pilot streamer is the streamer which kinds of takes the lead, and it moves forward and reaches or does not reach, but reaches very close to the earth first. And this pilot streamer, we are talking about an instant when the pilot streamer has been considerably lowered towards the earth and it is almost about to strike earth. So what you have is the pilot streamer has brought the negative charges from the cloud to a distance which is very close to ground, and this gap distance, this pilot streamer to earth, that gap is very, very highly stressed. And therefore, after that, what happens is this gap is bridged not by the pilot streamer, but by a return streamer, a heavy return streamer. So just as it is about to reach, there is a bridging of this very highly filled region between the streamer and the earth, and therefore a very large discharge is pumped from the earth to the ground. And this heavy return streamer, which discharges to earth all the negatively charged space beneath the cloud, that is what is very dangerous, because that carries the maximum current. What really happens is now you have a channel that is produced which is full of ionized particles, not neutral particles. That channel, that path has been created. And so when the return stroke strikes, it has a very easy path to the cloud. It has a low conductivity, high conductivity channel already formed, and it takes this path to the ground. So the path has been created by the pilot streamer, but the return streamer injects a very large quantity of current into the cloud, and it neutralizes the charge center. Now, when the first charge center is completely discharged, we must remember that in a particular cloud, there will be other charge centers. Not only that, there might be other charge centers in neighboring clouds. And so the next thing that happens is when the first charge center is completely discharged, there would be development of streamers between charge centers within the cloud. So you will see a discharge propagating from this initial charge center to the original charge center. You might also see discharges propagate from a charge center in a neighboring cloud to this charge center. And this is where you see the intercloud lightning. So we know that when we see, there are lightning of two types. One is the intercloud lightning, which remains in the sky, and then you have the clouds to ground strikes, which brings the charge from the clouds onto the ground. So these are the steps. So first charge center is completely discharged and you have a development of streamers between charge centers within the cloud. And then once this discharge connects up these two charge centers, then because there is already a low high conductivity channel to ground created by the first flash, this second charge center will also now discharge to ground along this original channel. So first there will be a discharge between two charge center, then the dart leader which will propagate to ground along the original channel. As soon as the dart leader is about to strike the ground, where again you have the negative charge has been lowered and distributed along the stroke channel, the heavy return streamer discharge of earth of negatively charged space between cloud just as before happens. So now the return stroke will connect to this charge center via this charge center to the other charge center and will discharge all the charge that is there in the second charge center. Now note this point that in the second, so after the first return stroke, when the second discharge happens, there is something called a dart leader. So any pilot streamer which leads the way along a previously ionized path in the second or subsequent strikes is called a dart leader because it moves forward very fast, because it already has the work done for it. So initially the step leader may be moving not so fast slowly, but when after the return strike, the second pilot streamer will move very fast and therefore it is called a dart leader. And the most important thing that to be noted is that it is the heavy return strokes. So one thing we understand, that is generally when you have a lightning strike, you do not have a single strike. Normally you will have several strikes and you may be able to count up to 40 strikes from one lightning. So one lightning strikes, a path is created, and then there are several subsequent strikes, and through those several subsequent strikes, all the charge that is in the cloud will be discharged to ground. It will not happen in one strike. So you will generally see several strikes together, one after the other, and it is the return stroke which is dangerous because the return stroke carries the largest quantity of energy. Number one. Number two is when the pilot streamer which lowers the charge towards the earth in the second or subsequent strikes is called the dart leader. This I have explained the mechanism of lightning considering that the cloud is negatively charged. It is also possible to have a downward positive ground flash. The mechanisms of downward positive ground flashes have not been studied in great detail, but their main features are qualitatively similar, except that instead of positive charge from ground, you have negative charge from ground, and you have positive charge on the cloud. So the charge polarity on the cloud and the ground is reversed, otherwise the process remains the same. So these are situations where you have downward strikes from the cloud to the ground, and this can be either a positive ground flash or a negative ground flash. So the lightning initiates from the cloud. However, the return stroke always comes from the ground. In this case, the lightning initiates from the cloud and the return stroke initiates from the ground. Return stroke always initiates from the ground. The return stroke is initiated when the charge on the ground object is high enough to initiate an upward positive streamer. So once these pilot streamer reaches very close to the earth, and the small gap distance between the pilot streamer and the earth is very small, the field is extremely high, that is when the return stroke is initiated. And this return stroke travels much faster along the previously established ionized channel. We already have the ionized channel. You don't have to do it as it goes. The current is very high. It is of the order of kiloamperes to 250 kiloamperes. The reason that lightning strikes are damaging, are dangerous, is mainly because of the high current content. Because when you have a very high current content, when you have any current flowing, there is a corresponding I square RT heat generated. And if the current is in the order of 250 kiloamperes, the heat that would be generated by a current carrying conductor, by a current carrying channel that is carrying 250 kiloamperes, the temperature will be extremely high. And the temperatures within the channel will be of the range of 15,000 to 200,000. 15,000 to 20,000 degrees centigrade. And that kind of temperature is what causes the high luminosity of the lightning channel. So it's a flash of lightning which kinds of blinds you. And that is because of the enormous quantity of light energy being dissipated apart from heat. And the most problematic thing is this channel causes explosive air expansion. So that is like a bomb, the explosion of a bomb. When a bomb explodes, the air around it receives a shock wave, and this shock wave propagates from the core of the bomb all around. Similar thing happens with the lightning strike. Because of that high current, the air around it gets heated up and it heats up instantaneously. So it's like an explosive air expansion. The air expands and a pressure wave travels, and this pressure wave, when it hits any object in its path, it's going to cause considerable damage. So it will cause mechanical damage because of the pressure wave. It will burn whatever is in its path because of the high heat. The flash is blinding. So that is how your lightning gets to be so dangerous. Return stroke is generally followed by several strokes at 10 to 300 millisecond intervals. As I have already mentioned, the leader of the second and subsequent strokes is called the dirt leader. Just as you have downward flashes, it is also possible to have upward ground flashes, and this would possibly be in cases where you have a tall structure. So for example, let's say you have a tower or a very tall tree, and because of the flux concentration, because there is a charge on the clouds and there is a field in the gap between the earth and the clouds, and at the tip of the tall structure, it is like a needle plate geometry. So there is very high local field intensification at the tip of the tower, and as a result, the air in this region begins to discharge. So that is how an upward ground flash is initiated, because an upward leader is initiated from a tall structure under the influence of the background electric field of the clouds. And then this leader propagates towards the clouds. The charge that will be there on this leader, it can be negative or positive. It depends on what kind of charge center you have on the clouds. If you have a positively charged center on the cloud, you will have a negative upward flash, and vice versa. And this flash will go upwards and it will negate, it will neutralize the charge center in the cloud, and this will lead to the initiation of a continuous current flowing from cloud to ground, and this will last for several tens to hundreds of milliseconds. This entire discharge process, by which the entire charge in the clouds will be dissipated to ground through a lightning flash which has been an upward ground flash which has been initiated at the tip of a tall structure, may last several tens to hundreds of milliseconds. And this also, as I said, can be both positive or negative. So you can have downward positive, negative, you can have upward positive, negative. Now, as I say, the most important consideration is that of the current. The lightning channel carries a huge quantity of current. Let us assume that there is a potential difference between the cloud and ground of 10 to the power 7 volts at the instant of breakdown. And let us say before breakdown, there is 20 coulombs of charge on the cloud. Now this charge will be dissipated through a high current, which will flow across this 10 to the power 7 volts potential difference. So that means a very large quantity of energy. The energy that will be released would be like 20 into 10 to the power 7 watt seconds, which is like 55 kilowatt hour. And of course, this energy may not be discharged by one stroke, but it will be discharged through one or more strokes, and most of the energy content will be in the initial strokes. The first two strokes will have the most energy. So that means in lightning, we are considering a very high energy discharge, and that is why lightning causes so much damage to its surroundings. If you look at this is a probability distribution curve for stroke currents, and as you can see, we have stroke currents as high as 200 kiloamperes, almost 200 kiloamperes, but this is taken from IC standards. But you see that there is also the possibility that there can be stroke currents which are much lower. You can have 10 kiloamperes, 20 kiloamperes, 40 kiloamperes, and the probability of such low magnitude currents is much higher. So if you're expecting a 20 kiloampere current, the probability is something like 35-40%. Whereas if you are expecting a 100 kiloampere current, the probability is much lower, something like 2%. Now, yes, we can have 200 kiloamperes or higher current magnitudes, but the probability will be considerably low, like 0.1 or 0.2%. But it is always possible to have even current magnitudes as high as 200 kiloampere. And that is what is dangerous. Now, how do lightning cause danger to the objects around it? And here I'm not talking about power systems, but just any object. Now, there are two principal ways by which lightning can interact with its surroundings and cause damage. One is, of course, a direct injection of current. So you have a point on the ground or a tall structure, and the lightning strikes directly to this point. As a result, as you can see, there will be considerable current flowing, considerable light, considerable heat. As a result, and there will be air explosion. So this can cause considerable structural damage and can even initiate fires. As you might have been hearing, there have been a lot of fires, lightning fires in California, which has been spreading like wildfire even in and around Oakland and San Francisco. And that is because of these direct strikes. The heat in the direct strikes, which causes the air to heat up and may cause any inflammable object to burn. In California, it's a dry bush. It is so dried out that it immediately kindles. The injected current may also enter into electrical and other conducting systems. Now, this direct injection of current and causing an object to burn can happen to any device. But when you have electrical and conducting structures, the damage can be even more. Because when you inject current into a system and it is connected with conducting, it is in a conducting system, it's part of a conducting system, then that current is going to be conducting through the network, and this injected current may therefore enter into the electric and other conducting systems of the structure. And this can cause damage and destruction of the electrical system. So even if your whole house does not burn down, your whole electrical wiring might be completely defunct, may become defunct. So this is when you have a direct strike. But remember, direct strike is not very common. Especially in buildings or structures, you would have a lightning arrestor. So the lightning arrestor provides an alternate preferential pathway for the lightning. So it's generally taller than your building. So when a lightning is lowered, it will preferentially strike directly the lightning arrestor. And so therefore, direct strike to any building or any device is unlikely. But we do see a lot of problems arising due to lightning strike, even though we may have lightning arrestors. And that is because of indirect stroke. So probably the stroke is occurring to some other structure. not to the structure that we're interested in, but it is in the vicinity of the structure. Now, because of this lightning strike and because of this high current flowing, there will be a very large electromagnetic field which is generated. And this electromagnetic field which is generated by the lightning flash will spread all around, and it will induce voltages in conducted structures. So if you have electrical systems, even if the electrical system does not take a direct hit, but if a lightning hits nearby, there will be induced voltages in the conducting system, and these induced voltages will be very high. And as a result, there will be a large current flowing through the electrical network, which will cause damage to the electrical system of the structure. So the electromagnetic field generated by the lightning flash induces large voltages in various electrical systems of the structure, irrespective of whether it is provided with an external lightning protection system or not. And the disturbances and damages any sensitive electronics. Not only sensitive electronics, electrical damage may also be there. So direct strike may be prevented, but even with indirect strike, the electrical system may be completely demolished. So these are the two principal ways in which lightning can affect the system. Now, therefore, when we want to design a power system, the first thing we have to figure out is we have no control over the lightning. We do not have any control over the lightning magnitudes. We do not have any control over how many times lightning may strike. But we can estimate that before we design the system, because we have what is called the isochironic map of the world. So what does the isochironic map give us? The isochironic map gives us the frequency at which we can expect lightning to occur in a certain geographical region. And that is, so what we will estimate is, we will estimate a quantity called the ground flash density. That is, what is the density of number of lightning flashes that can strike a unit area. So the ground flash density is defined as the number of lightning flashes that strike a unit area in a given region in a year. So as you can see here, of course, this gives you thunderstorm days. I'll come to that later. Let's say in this region in Africa, you can see this dark region. So what this information is that in this region, if you consider a unit area of the land, what is the expected number of lightning flashes striking that unit area in a given year? That is measured as the ground flash density. How do you measure that? You can estimate the ground flash density in any geographical region by counting the number of lightning flashes that strike the ground in that region. And you can count that there are various ways of counting lightning flashes. It can be, you might be using lightning flash counters, you might be using lightning location systems. So there are various devices by which lightning can be counted, and by counting the number of lightning flashes that strike the ground in that region every year, you will have what is called the ground flash density. So that gives you an idea about how frequent lightning flashes are in that particular region. Now, even though we are in a position to count the lightning in a year, most of the time engineers will use, instead of actually counting the lightning discharges, they will use the count of thunderstorm days. As you can see in this picture, here what you have is a map of the thunderstorm days. And this is a geographically, dependent factor. You see the lighter regions correspond to very low thunderstorm days, very few number of thunderstorm days, and the darker regions are very high. Now, what is a thunderstorm day? A thunderstorm day is normally defined as the local calendar day in which thunder is heard by meteorological observers. So the meteorological department keeps a count of the number of times, number of days on which thunderstorm is heard in a particular region. So as you can imagine, in these dark regions inside Africa, you hear thunder very frequently, as you can see. The darkest regions correspond to 140 to 200 plus. That means out of 365 days in a year, on 200 days, you are likely to hear thunder. Whereas if you're in these regions, the white regions very close to the pole, or even here near Europe, you might be hearing thunder on only 1 or 2 days in a year. So this is a map which is available already with the engineers. The engineers have the thunderstorm map of the world, and therefore they prefer to work with this data. Now remember, there is one problem with this. We are counting the number of days on which we hear thunder, but we are not taking into consideration the intensity of the thunderstorm. We just hear thunder. It may be a very loud clap of thunder. It may be a tiny whimper. We give it the same priority, same importance, which may be unscientific. Also, we do not consider the number of times thunder is heard in a day. So sometimes we have here days when you hear the thunder all through the day. Or there might be one thunderclap in the morning and then the sun comes out. We are not differentiating between these two kinds of days, so we are losing some information. However, despite that, we can consider the number of thunderstorm days we take from the thunderstorm map of the world, and from that we can estimate the ground flash density as Ng equal to Td to the power B flashes per kilometer square per year. So this would be the ground flash density expressed in terms of per square kilometer per year. So many number of flashes, A and B are exponents which have to be obtained geographically, and this is obtained from the number of thunderstorm days, Td. So this gives us an estimate about the lightning activity in a given region, and therefore you would design differently if you are designing a power network in the center of Africa, or you are designing it near the poles. Your considerations will be quite different because you would expect a different level of lightning over voltage. Next, we will talk about the effect of lightning on power systems. Now, before we actually will see the same kind of thing that we see in non-electrical devices. A lightning flash, when it strikes a ground, it will generate a horizontal electric field, and this horizontal electric field will decrease with distance. So sometimes what you might see is you might actually see an electrical discharge propagating along the ground. And this is called a surface discharge, and this surface discharge can also result in fires. This is something that I already mentioned. As for electrical installations, lightning can create overvoltages in electrical installations, either by direct attachment of lightning, which is a direct strike, or as a result of the coupling of the electromagnetic field with the electrical device from a remote lightning, which is your indirect strike. So very similar to what we have just discussed in terms of non-electrical devices. And of course, in addition to induced electromagnetic strikes, lightning may strike far from the object, and the surge can be conducted to the object via power line. So if you have connectivity, more damage is likely. So it's the same kind of thing that you would see in case of an ordinary object. Now let us see what exactly happens in the power systems when the power system begins to interact with the lightning. Now, when there is a conductor, the power transmission network is there, and over that you have a cloud full of charges, let us say. It is very highly charged. So it will not only, these charges on the cloud will not only induce charges on the ground below it, but it will also induce charges on the transmission wires. So there will be induced charges. Now the cloud moves very slowly. When the charge moves, the induced charges will be just below the cloud. So the induced charges, the position of the induced charges will move. And when the position of the induced charges move, that means there is a redistribution of charges on the transmission lines along the conductor. And whenever there you have movement of charges, you have current you have. It's also possible. So this will give rise to currents. So you don't really have a catastrophic failure. But simply because of the movement of the clouds, you may have stray currents arising in the transmission network. And you can also, this can even give rise to, if you have a lot of induced charge on the transmission line, this can even give rise to momentary partial discharges. Apart from that, there is of course the case of where you have a lightning strike. I'm not going to consider the case of a direct strike because direct strikes are rare. We generally protect our systems against lightning strikes, but we know what will happen when we have direct strikes, and we know what will happen when we have direct strikes. There will be considerable damage to the system because of charge being injected into the system and a lot of current flowing. Apart from that, we would like to look at the various ways in which the power system components interact with the lightning when there is an indirect strike in the vicinity of the lightning strike.